But anyway, we're going to do that. I think this is actually the opposite. I think this induction proof actually helps you actually really understand things. And this is something that we've talked about before. And I might get an eye roll. Good thing all your cameras are turned off. And that is prove that every natural number is even or odd. Yeah. Remember this guy? Remember this really complicated, stupid proof that we use contradiction and a weird way to prove this? Don't leave the screens. It's all right. It's all right. It's a safe place. This is actually being a lot easier with induction. I wanted to show you that you could do it with contrapositive, but induction is the real way to do this. And actually, doing it with contradiction kind of shows you that, hey, the proof technique you use really matters, right? You can work smart, not hard. So here, here's the idea. The formal claim of this would be that for all n and the natural numbers, n is even, or I'll say n even, or n odd. And it should be noted that the natural numbers are simply all the integers that are bigger than or equal to 1. So this totally fits our form of trying to prove something for all integers greater than or equal to some a. The a here just happens to be 1. Let's just get into it and we'll talk about things. So the beginning of a induction proof always works the same. You don't have to think that hard. You say proof by weak mathematical induction. Proof by weak mathematical induction. And then from there you say, on n, that's the variable we're kind of going through here, like as n, we're ranging in. And their base case. And remember here in our base case, what we want to do is we want to show that P of 1 is true. Because we're trying to show it's true for everything bigger than or equal to 1. So you want to start at the bottom, show P of 1 is true. I.e., in this case, we want to show that 1 is even or odd. Real simple. I'll say let n equals 1. Note 1 equals 2 times 0 plus 1. Since 0 is an integer, 1 is odd by definition. So 1 is even or odd. It's odd in this case. Thus, the base case holds. Real simple. 3 lines to prove that 1 is odd, but we didn't. Here's the inductive step. Remember, base case is computational. Inductive step is the more clever, interesting part. So in the inductive step, we want to show for all n bigger than or equal to 1, P of n implies P of n plus 1. In our particular case, we're trying to show that for all n greater than or equal to 1, if n is even or odd, then m plus 1 will be even or odd. So why is that true? Let's think about that, right? If n is even or odd, why is n plus 1 even or odd? So what do you think we should do with n, first of all, here? If we know n is even or odd, what's kind of a good proof technique to simplify things some?
Uh, either 2k or 2k plus 1 maybe.
Totally, we're going to do that. I say even broader proof technique, let's just divide into cases, right? Let's look at each case
Okay.
and see what happens. And so it sounds simple. I mean, this is problem solving 101 right here. These are really important problem solving ideas. The idea of you have a problem that's too hard to solve, break it into smaller problems and try to solve each of those. So a case of, and by the way, that's a recursive thing. Each of those smaller problems still too hard, break the smaller problems into smaller problems. So case one, if we have an even, well then n's gonna equal 2k, right? So what do we know about n plus 1?
It's odd.
Yeah, then n plus 1 is going to equal 2k plus 1, which is odd. Case 2, n is odd. Like Tor said, we can write that as 2, n equals 2k plus 1. What do we know about n plus 1 then?
It's 2k plus 2, and then you could take out a 2.
Exactly. And so since k plus 1 is an integer, because k is an integer, 1 is an integer, integers are closed under addition, that means this is even. So this is Domino's ass finest. That's absolute finest. Right here, we started with n even, right? And we show, or we start with n even or odd. If n's even, well, hey, if you add 1 to that, you get an odd number. If n's odd, you add 1 to that, you get an even number. That's the chain reaction. 1's odd, so 2's even, meaning 3's odd, so 4's even, 5's odd, 6 is even. The point is, every single integer there is hit, and every one of them has to be even or odd, none are skipped. That's so much simpler than whatever we were trying to do before, with like weird contradiction of like, let's take all the even numbers less than this and figure out what happens. So much simpler. And it makes sense. And the reason this kind of makes sense is because inherently the natural numbers are inductive. They're actually defined inductively as a thing you don't even know, but they are. So that kind of makes sense though, because like each even number or each natural number is just 1 plus the natural number before it. So you start at 0, add 1 to get to 1, add 1 to get to 2, add 2 to get to 3. It's a recursive inductive definition. So it kind of makes sense that that an inductive proof might work on it. So let's get to proving it. So that's the idea. Let's make it formal. So remember, trying to prove this claim for all n greater than or equal to 1, if n is even or odd, then n plus 1 will be even or odd. This is a universal conditional statement. So the way you prove that is you first just let n be something in the domain, something arbitrary particular, assume the hypothesis, you need to show the conclusion. So let's say let n be any arbitrary / particular integer such that n is greater than or equal to 1. Assume n is even or n is odd. I could break into cases. Case 1. I didn't like the look of that. Case 1, there we go, much better. N is even. Then, by definition, n equals 2k for some integer k. For some integer k. Thus, n plus 1 equals 2k plus 1 by adding 1 to both sides. Since k is in Z, n plus 1, which equals 2k plus 1, is odd by definition. So in case when we showed that if n is even, then n plus 1 will be odd. It's got to be. And I'm actually going to erase this to save some room. I'll keep the important bits. Be cool? So if n is even, then n plus 1 will eventually get to n plus 1 is odd. Case 2. N is odd. If n is odd, then n equals 2k plus 1. And actually, I'll say 2t plus 1 for some t and z. The reason I'm doing that is because I used k above. Technically, it's okay. It's like in computer science, if you have like two different methods, you can use the same local variable twice. That's fine. Very similar concept here, but just to avoid confusion, I'll make them different. It is odd, then n equals 2t plus 1 for some t and z. Then n plus 1 equals 2t plus 1 plus 1 by adding 1 to both sides, and that equals 2t plus 2 by associativity, and that equals 2 times t plus 1 by factoring out a 2. Then, since t and 1 are in z, and z is closed under addition and multiplication, or actually z is closed under addition, t plus 1's in z. Thus, n plus 1, which equals 2 times t plus 1, is even by definition. So starting with n is odd, then n is going to be 2t plus 1. So you add 1, you get 2t plus 2. Factor out the 2, you get 2 times t plus 1. So n plus 1 is even. Starting with n even, you get n odd. Starting with n odd, you get n even. And again, I'm going to erase this to make room, but it's okay. Perfect. So starting with n odd, we do our proof. This is like in computer science when you take a method and you like collapse it so you don't have to look at it. Then n plus 1 is even. Thus, in either case, n plus 1 is even or odd. So you start with n even or odd, right? If you ever get to a point where n's even or odd, then the next number after that will also be even or odd. Therefore, the next number after that will also be even or odd. The next number after that will also be even or odd. That starts your chain reaction where everything after that's even or odd. And luckily, we have a base case of n equals 1, and that's even or odd. It's odd, so it works out. So conclusion, therefore, for every natural number n is even or odd. Oh. Square, you're done. Oh, nice. Beautiful. This is the exact power of induction right here, right? We had a proof that before we said, wait, this is really simple. Everything's even or odd, but it was really, really hard to prove. Like, how would you actually show that there can't be a single number out there that is skipped by the evens and odds, just somehow is missed? And this is how you show it. You show that every integer is 1 plus the integer before it, and that necessitates that it's even or odd. It just keeps going like that. It's even or odd, even or odd, even or odd, even or odd, even or odd. Any questions? All right, so I'll do one more example and call it a day. Now, note, by the way, that we could also obviously show that 0 is even, and then we could kind of do like the reverse of this argument on the negative natural, or like the negative numbers, negative integers, or you could even just say that, oh, every negative number that's -1 times a natural number, and that's going to go the same direction as that number is, right? Like 2's even, -2's even. 3's odd, -3's odd. So you can kind of prove it that way. The point is the same idea holds for all integers. I just did it for natural numbers to keep things a little cleaner because we're just learning.